as they say it, a whiz kid with a very powerful idea. Max Lawhen shares his story in tonight's Someone to Know.
CERN has actually opened a portal to another dimension. The world's smartest kid, Max Lawhen, has been saying for ages that CERN could open a portal to another dimension using its Large Hadron Collider, and now people are seeing it with their own eyes.
It's so stunning,
It's
like
an
as a
incredible
physical
piece of work.
thing. That this, I mean, how large is it? How large is
It's
the loop?
it's 27 kilometers, so what's that, about 16 miles?
16 miles, and it's a circular.
On June 24th, a picture of swirling clouds over the LHC went viral. People are now saying CERN's Awake experiment has opened a doorway to another world. But is it true? Has CERN really opened a portal to another dimension? The brightest minds. The universe is a mind-blowing place. It is huge, mysterious, and full of surprises. Think about it. We are tiny specks in this vast cosmos, and yet we are curious enough to try and figure it all out. The more we discover, the more we realize how much we don't know. From black holes to the possibility of multiple dimensions, the universe is full of wonders that keep scientists and dreamers awake at night. One thing that is clear is our never-ending thirst for knowledge. 100 years ago, we didn't even know galaxies existed outside our own. Now, we are finding thousands of them, each full of billions of stars. We have learned about the Big Bang, the event that started it all about 13.8 billion years ago. We have even sent probes to the edges of our solar system, like Voyager 1, which has been traveling through space since 1977, but that is just scratching the surface. Scientists are constantly exploring the fundamental nature of reality, from the tiniest subatomic particles to the vastness of galaxies. This thirst for knowledge led us to the discovery of the God particle. The Higgs boson, sometimes called the God particle, was discovered in 2012 by scientists at CERN, or the European Organization for Nuclear Research. They used what they call the Large Hadron Collider. Now, this God particle is important because it explains why other particles have mass. Without the Higgs boson, the universe as we know it would not exist, because particles would not hold together to form atoms. So what exactly is the Higgs boson? To understand it, you have to imagine the Higgs field. The Higgs field is an invisible energy field that permeates the entire universe. Particles gain mass by interacting with this field. The more a particle interacts with the Higgs field, the heavier it becomes. The Higgs boson is essentially a manifestation of this field, a particle that we can detect to prove the field's existence. The existence of the Higgs boson was confirmed using the LHC, correct? But do you know what LHC is? The LHC is the world's largest and most powerful particle accelerator, situated near the border of France and Switzerland. It is a massive circular tunnel, about 17 miles in circumference, located about 100 meters underground. The LHC was built to smash particles together at incredibly high speeds to study the fundamental components of matter. In the LHC, protons are accelerated to near the speed of light and then collide head-on. These high-energy collisions mimic conditions just after the Big Bang, allowing scientists to observe particles that don't normally exist in nature. In short, the discovery of the Higgs boson was groundbreaking. It was a major breakthrough. But this monumental achievement also made the way for something far more unsettling, according to one of the world's youngest and brightest minds, Max Lawhen. What did Max have to say about CERN and its Large Hadron Collider? Max Lawhen and CERN. Max Lawhen is a name you might have heard. Born in 2002 in the United States, Max showed a genius-level talent for science and technology from a very young age. By the time he was 13, he had invented a free energy device. Yes, at 13. This invention was aimed at creating a sustainable energy source that could change the way we live. This put Max in the spotlight and started his journey to fame. While on one hand, Max kept inventing gadgets and devices, he also started contemplating the big questions about the universe and how it works. One of his most talked about ideas is about CERN, the European Organization for Nuclear Research, and their giant machine, the Large Hadron Collider. The LHC is the world's biggest and most powerful particle accelerator. It is like a 17-mile-long tunnel where scientists smash tiny particles together at nearly the speed of light. While the LHC was used to discover the Higgs boson, Max believes it might have done something even crazier and way more dangerous. He claims that the experiments at CERN have actually opened a portal to another dimension. Max says these high-energy collisions have caused a tear in the fabric of our reality. It has created a doorway to parallel universes. He thinks this is not just a wild idea, but something that has already happened, and that it has been changing our world in ways we are only starting to see. To understand Max's theory, we need to talk about parallel realities and the multiverse. The multiverse theory is that our universe is just one of many. It means countless universes exist at the same time, each with different versions of reality. Max thinks the LHC's experiments have messed with the balance between these universes, causing strange things to happen in our own world. One piece of evidence Max points to is the Mandela effect. We will tell you what it is in a moment. For now, we want to let you know that Max even claimed that when the LHC smashes particles together, it creates conditions similar to those right after the Big Bang. These conditions are so extreme that they can potentially tear space-time. It can lead to things like micro-black holes. Are you thinking, why isn't anyone else freaking out about this, right? Well, everyone is. Most scientists think these black holes would disappear instantly, but Max argues they might be doing more than we think. He suggests these collisions could be making tiny portals to other dimensions, portals that might not close completely. Max also talks about how our reality and our consciousness are connected. He believes that changes in the universe can affect how we experience the world. If the LHC has really opened a portal, it could be changing our world in subtle, strange ways that we are just starting to notice. Max's claims have started a lot of debate. Many scientists say there is no real evidence that the LHC has opened portals to other dimensions. They argue that while Max's ideas are interesting, they are still just theories without solid proof. But Max's ideas have definitely caught the public's attention. He has a way of making complex science easy to understand and exciting. Whether or not his theories about CERN and the LHC are proven true, they have definitely made people more curious about the mysteries of the universe. And when people start talking about these things, controversies are bound to emerge. Have you heard about these shocking controversies? Controversies. The discovery of the Higgs boson and the powerful capabilities of the Large Hadron Collider have led to many debates and questions. One of the most intriguing and controversial ideas is that CERN's experiments could be opening portals to other dimensions. But that's not all. There are several other controversies that have formed around CERN. Yes, we talked about the Mandela effect, but we want to prove to you that it is not just a controversy. This phenomenon occurs when large groups of people remember events differently than how they actually happened. You see, some people recall Mandela dying in prison in the 1980s, even though he passed away in 2013. The Mandela effect covers a range of such anomalies. People remember famous lines in movies differently, logos and brands appearing altered, and even historical events seem out of place. Why does this matter in the context of CERN and the LHC? Well, some theorists, including Max Laughlin, believe that the high-energy collisions at CERN might be altering our reality. Sometimes, this could lead to tears or distortions in our reality, causing shifts that result in these collective memory discrepancies. The idea here is tied to the multiverse theory, which suggests our universe is one of many parallel universes existing simultaneously. If the LHC's experiments create conditions similar to those right after the Big Bang, they might be opening tiny portals to these other universes. When these portals open, they could potentially allow bits of these other realities to mix with ours, leading to the strange phenomena people remember as the Mandela effect. This is a mind-blowing phenomenon that Max Laughlin noticed about CERN. Another big controversy revolves around the idea of creating black holes. Back when the LHC was about to start its first run, some people were worried it could create a black hole capable of swallowing the Earth. The fear was that the energy produced during particle collisions might be enough to create a stable black hole. While this idea sounds like something far-stretched, it caused a lot of concern. Physicists, however, have explained that any black holes created by the LHC would be incredibly tiny, and it would evaporate almost instantly due to a process called Hawking radiation. In other words, these black holes would not last long enough to do any harm. Despite these reassurances, the idea of creating black holes at all has horrified many people. The concept of altering reality and opening portals also ties into another controversial idea: time travel. Some people theorize that the LHC could somehow affect time, either slowing it down, speeding it up, or even allowing for backward time travel. This idea stems from the fact that high-energy physics deals with conditions and particles that existed at the dawn of the universe, where the laws of physics as we understand them could behave differently. Time travel theories are largely speculative, and there is no solid evidence that the LHC has any capability to affect time in such ways. However, the very nature of particle physics and the unknowns involved leave room for wild theories and speculations. Another area of controversy is the use of massive resources for such experiments. The LHC is one of the most expensive scientific instruments ever built, costing around $4.75 billion. Critics argue that the money could be better spent on more immediate human needs, like healthcare, education, and poverty alleviation. Supporters counter that the knowledge gained from these experiments could lead to breakthroughs that benefit humanity in the long run. The secrecy and complexity of CERN's experiments also fuel controversies. The technical jargon and highly specialized knowledge required to understand what is happening at the LHC mean that for most people, it is all a bit of a mystery. And when there is a gap in understanding, it can lead to mistrust and the formation of conspiracy theories. Some conspiracy theorists even claim that CERN is hiding the true extent of its experiments and their potential impacts on our world. For example, the Awake experiment at CERN, which involves accelerating particles using a plasma wake field, has caused fear among some that it could lead to uncontrolled consequences. On one hand, the scientists at CERN are transparent about their goals and safety measures, but on the other hand, the highly technical nature of their work leaves room for misunderstandings. Conspiracy theories also came up with another wild claim. Some people believe that by conducting these high-energy experiments, scientists are tampering with the fundamental aspects of nature in ways. They say the scientists are playing with God and His creation, and it could have unforeseen and potentially disastrous consequences. This fear comes from the fact that much of what is being discovered is still not fully understood, even by the scientists conducting the experiments. The only way to debunk these theories and comfort those who are concerned is by learning about the actual breakthroughs and discoveries that CERN has made. By understanding the real science behind the LHC and its experiments, we can separate fact from fiction and appreciate the incredible advancements in our knowledge of the universe. So what discoveries and breakthroughs have emerged from CERN's research? Breakthroughs. One of the most famous discoveries made by the LHC is the Higgs boson. We have already talked about its incredible discovery and how it has changed our understanding of the universe. After the Higgs boson, a mind-blowing discovery from the LHC is the identification of X particles. These particles, named for their mysterious nature, were detected among billions of other particles within the quark-gluon plasma created during high-energy collisions. This plasma is similar to the state of the universe just microseconds after the Big Bang. X particles are believed to have formed during this early stage of the universe, making them incredibly valuable for understanding the conditions of the primordial universe. The quark-gluon plasma is a state of matter that existed when the universe was extremely hot and dense. Quarks are the building blocks of protons and neutrons, and gluons are the particles that carry the strong force. So, in the quark-gluon state, quarks and gluons were not bound together into atoms, but floated freely in a sort of particle soup. By recreating this plasma, scientists can study how these fundamental particles interacted and formed the complex structures that make up our current universe. After that, the LHC has also made great advances in studying antimatter. Antimatter is the opposite of regular matter. For every particle, there is a corresponding antiparticle with the opposite charge. One of the mysteries in physics is why there is so much more matter than antimatter in the universe. Experiments at the LHC have provided insights into the subtle differences between matter and antimatter, which could help explain this imbalance. If we try to understand antimatter better, we get to learn more about the fundamental questions about the universe's origin and also its practical applications. For example, positron emission tomography or PET scans in medical imaging rely on antimatter. By studying how antimatter behaves, we can improve these technologies and potentially develop new ones. Not stopping at this, the LHC has recreated conditions similar to those just after the Big Bang by producing quark-gluon plasma. This state of matter existed when the universe was only a few microseconds old. By studying this plasma, scientists can learn about the strong force that holds atomic nuclei together. Observations from these experiments help us understand how the universe evolved from a hot, dense state into the complex structure we see today. The strong force is one of the four fundamental forces of nature, alongside gravity, electromagnetism, and the weak force. It is responsible for holding quarks together to form protons and neutrons, which in turn make up atomic nuclei. By examining how quarks and gluons behaved in the early universe, scientists hope to learn about the mechanisms that allowed matter to form and stabilize as the universe cooled. Now, one of the coolest explanations by CERN was for the study of supersymmetry. It is a theoretical framework that tells us that each particle in the Standard Model has a heavier superpartner. If we discover these superpartners, we will be able to solve many puzzles in physics, including the nature of dark matter. Do you know what that is? Dark matter. Dark matter is one of the most mysterious and intriguing subjects in cosmology. It is a type of matter that does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects. Despite its elusiveness, dark matter is believed to make up about 27% of the universe. The Large Hadron Collider at CERN is currently being used to understand dark matter. The LHC is the world's largest and most powerful particle accelerator. So CERN is using this power to search for dark matter particles. While we cannot see dark matter, we know it is there because of its gravitational effects on visible matter. For example, galaxies rotate faster than they should based on the amount of visible matter they contain. This discrepancy suggests there is something else, something invisible, providing additional gravitational pull. That is dark matter. But why do we need to learn more about dark matter? First, it helps explain the structure and behavior of galaxies. Without dark matter, galaxies as we know them wouldn't exist. The gravitational pull from dark matter holds galaxies together and prevents them from flying apart due to their rotational speeds. Second, dark matter influences the formation of galaxies. During the early universe, dark matter provided the scaffolding around which normal matter gathered. Without dark matter, the gravitational pull would not have been strong enough to form galaxies, stars, and planets. Third, dark matter affects the cosmic microwave background, which is the afterglow of the Big Bang. The distribution of dark matter in the early universe influenced the temperature fluctuations in the cosmic microwave background. If we study these fluctuations, scientists can infer the properties of dark matter and its role in cosmic evolution. The LHC is trying to discover dark matter particles by recreating the high-energy conditions of the early universe. When protons collide at nearly the speed of light, they break apart into their constituent particles, creating a shower of new particles. Some of these particles are familiar, like quarks and gluons, but some could be entirely new, potentially including dark matter particles. One theory is that dark matter consists of particles called weakly interacting massive particles. WIMPs are hypothetical particles that interact with normal matter through the weak nuclear force, which is much weaker than electromagnetism and gravity. The LHC can potentially produce WIMPs during collisions. Scientists then look for signs of these particles by analyzing the debris from the collisions. If WIMPs are produced, they would escape the detector, creating an imbalance in the energy and momentum observed in the collision aftermath. This imbalance could be a signal of dark matter. But why are we telling you all of this now? Why is all this physics important for you to understand as a viewer? Well, the reason is that with every new discovery and theory, there is a need for more experiments and more particle collisions. Each groundbreaking idea about the universe, whether it is about dark matter or supersymmetry, needs to be tested and proven through high-energy collisions in the Large Hadron Collider. This means there will be an increased frequency and intensity of these collisions to study new insights. But with increased collisions come more chances for unexpected phenomena, including those that some fear could lead to the creation of black holes or alternate realities. For example, to prove the existence of dark matter particles like WIMPs, or to find evidence of supersymmetric particles, millions or even billions of collisions are necessary. Each collision is like a roll of the dice. The more you roll, the higher the chances of hitting the jackpot. However, these high-energy collisions also bring about concerns. One such concern is the creation of micro-black holes. According to some theoretical models, the energy produced in these collisions could be sufficient to create tiny black holes. But don't worry yet. Most physicists agree that these black holes would be harmless and evaporate almost instantly due to Hawking radiation, but the idea is still fearful. What if, by some rare chance, these micro-black holes don't behave as expected? Could they grow or interact with our environment in unpredictable ways? Another worst-case scenario is the creation of alternate realities. This ties back to the multiverse theory, which posits that our universe is just one of many. If these collisions can indeed open any portals, even momentarily, it raises questions about the nature of reality and our place in the cosmos. These concepts might sound like science fiction, but this is reality. The potential risks are taken seriously, but so are the safeguards. CERN has extensive safety protocols to make sure that their experiments do not pose a threat. The benefits of these experiments, which are advancing our understanding of the universe and potentially leading to revolutionary technologies, are considered to far outweigh the risks. Increased research and more frequent collisions at the LHC mean we are on the verge of potentially revolutionary discoveries. Each collision could bring us closer to understanding dark matter, or unlocking the secrets of supersymmetry, or even revealing entirely new aspects of physics. However, this also means stepping into uncharted territory where the rules of the universe could surprise us. So, on one side we have the Large Hadron Collider. But don't you think there might be other devices out there, or even those being built, that could pose even more damage or threat? Future prospects. If you thought the Large Hadron Collider was impressive, wait till you hear about what's coming next. CERN is going to introduce its new device soon, a bigger and much more powerful Large Hadron Collider, which is named Future Circular Collider (FCC). The FCC is set to be a 100-kilometer ring. That is more than 3 times the size of the LHC's 27-kilometer circumference. This monster of a machine is designed to collide particles into each other at mind-blowing energies, which can reach up to 100 teraelectron volts, compared to the LHC's 14 TeV. What does this mean? Basically, it is like going from a matchstick to a blowtorch. The FCC will let scientists dig even deeper into the universe's building blocks, looking for answers to those really big questions. One of the main goals is to study the Higgs boson in much greater detail. With the FCC, we will be able to produce Higgs bosons at a much higher rate, which will allow researchers to really figure out what particles have mass and how the Higgs field operates. Plus, who knows? We might even discover new particles or forces that we didn't even know existed. Supersymmetry, dark matter, anything would be possible. And there is more than that. The FCC is not the only thing the scientists are working on. There is also the International Linear Collider on the drawing board. Unlike the circular FCC, the ILC is a straight collider, literally. It will accelerate particles in a straight line, which could give us cleaner collision data since we won't have to deal with the same energy loss issues that come with bending particles around a curve. We are also going to have a compact linear collider. This collider also goes for the linear approach, but aims for even higher energies than the ILC. Both of these projects will push the boundaries even further. So what's the big deal with all these new colliders? Well, more powerful accelerators mean more chances to discover something truly groundbreaking, and also more chances to open up a portal or create black holes. While the idea of creating black holes or opening portals to alternate realities might sound cool, the truth is, this is very dangerous. The more we push these machines, the more we need to be aware of what could go wrong and what could go incredibly right. Even if theories like Max Laughlin's about CERN opening portals to other dimensions are not true right now, who's to say they won't be soon? Just recently, a picture of some really weird and electric clouds swirling over CERN went viral. It started all kinds of wild speculation. People have long spun theories about CERN summoning Satan or crashing asteroids into Earth. As we keep pushing the envelope with more powerful experiments, those conspiracy theories might just become true. What do you think? Should we keep pushing the boundaries and risk it all, or should we stop using these colliders? Let us know in the comments below. If you want more mysteries uncovered, go ahead and like this video and subscribe to the channel, because we have got a lot more of this. Thanks for watching. Goodbye.